Hello everybody, welcome to our lesson. Today's topic is induced EMF and current. At the end of the lesson you'll be able to explain Faraday's experiments, define induced current and EMF, and also define electromagnetic induction. Before we start the lesson, let's recall the definition of an EMF. Electromotive force, shortly EMF, is a potential or an energy per unit charge measured in volts. So, we've already talked about one of the biggest discoveries, that electric currents can create magnetic fields. And once scientists had figured that out, they wondered if the opposite was also true. Could magnetic fields create or induce an electric current? Many physicists designed experiments to detect electric currents induced by magnetic fields, but they kept coming up empty. That is until two physicists, Joseph Henry and Michael Faraday, both on their own, figured out what was happening. It turns out that magnetic fields do induce electric currents, but only under certain circumstances. In his attempt to produce an electric current from a magnetic field, Faraday used an apparatus like shown in the picture. A coil of wire was connected to a battery. The current that flowed through the first coil produced a magnetic field that was intensified by the iron core. Faraday hoped that by using a strong enough battery, a steady current in the first coil would produce great enough magnetic field to induce a current in the second coil. This second circuit contained a galvanometer to detect any current, but this circuit doesn't contain a battery. And when Faraday discovered in 1831 that magnetic fields induce electric currents, he got kind of lucky. Now let's try to do this experiment on our own using Phet Simulations and try to observe what Faraday did almost 2 centuries ago. We have the first coil, which is connected to a battery, and the second coil, which is connected to a voltmeter. Okay, we already set up a current through the first coil of wire. We can see it by the motion of electrons. So, see the motion of electrons, it means that currents are passing through this coil. And this first coil generates a magnetic field. As we said, Faraday expected that the magnetic field from the first coil would produce a current in a second coil, and you see there is no current in the second coil. That was probably pretty disappointing at first, but then Faraday noticed something weird. When he turned the current on and off at the first coil, there was a brief spike of current in the second coil. Look at the arrow of the voltmeter, it moves a bit. We can have better visualization if I replace the voltmeter with a bulb. Do you see the short light from the bulb? It means that the current is produced through the second coil, but it happens only at instant while the current is changing from off and on and back again. Faraday realized that he'd been looking for the wrong thing. A constant magnetic field didn't cause an electric current in a loop of wire. Only a changing magnetic field did. This was not the only experiment Faraday carried out to prove that electricity can be generated from magnetism. He did numerous experiments not only to demonstrate this phenomenon, but also to develop a good conception of the processes involved. One of the experiments performed by Faraday in that important year featured a permanent magnet and a galvanometer connected to a coil of wire wound around a paper cylinder, similar to those illustrated in this picture. Now, let's go to the Phet Simulations again to study Faraday's experiment in detail. We have a coil of wire connected to a voltmeter and a bar magnet, similar to what Faraday had. From previous experiment, we already know that constant magnetic fields, when a bar magnet is in stationary, do not produce an electric current through the coil. Let's turn on the magnetic field lines of a magnet to have better sense. And let's turn on the electrons. And now let's drag the bar magnet back and forth inside of the coil. And you can observe that voltmeter linked to the coil only indicates the presence of a current when the magnet is actually in motion. Also, note that its needle deflects in one direction when the magnet is moved into the coil and in the opposite direction when it's dragged out of the coil. That same effect can be observed if you move the coil towards the magnet. Another interesting observation: when the north end of the magnet enters the coil, electrons that travels around the coil in a clockwise direction, and it means that direction of current is counterclockwise, because motion of current and electrons is opposite to each other. And when the magnet is pulled out of the coil, the direction of electrons reverses. Current has direction in clockwise. So if magnet moves towards a coil, the direction of the current is counterclockwise, and if magnet is pulled out of a coil, the direction of current is clockwise. Let's flip a pole of a magnet to see how things change when the south end of the magnet, exhibiting different field lines, interacts with the coils of wire. You see that the results are absolutely opposite. When the south end of the magnet enters the coil, current is clockwise direction. When the magnet is pulled out of the coil, current reverses counterclockwise. Okay, let's make a conclusion from Faraday's experiment. If the north end of a magnet moves toward the coil, the direction of the current is anticlockwise. If it moves out of the coil, the direction of the current is then clockwise. And if we flip the polarity of the magnets, if the south end of a magnet moves toward the coil, you see current is now clockwise. And if the south end of a magnet moves out of the coil, the current is anticlockwise. Okay, now let's define the induced EMF and induced current. Induced EMF is the electromotive force produced by change in magnetic field, and induced current is the current produced by change in magnetic field. And all this process we did are called electromagnetic induction. Electromagnetic induction is a process of production of an EMF and current by changing magnetic field. So the process in Faraday's experiments are called electromagnetic induction. Well, this is the end of the lesson. If you like our video, please subscribe and share. Thank you.